Okay, heat in changes of state. Now, when we're talking about the heat of fusion, that means heat going from a solid to a liquid, so fusing to a liquid. Heat of solidification is going from liquid to a solid. What is the heat required to go into a liquid to make it a solid? Or really, what is the heat taken away that has a liquid go to a solid? Heat of vaporization, what is the heat required to put a liquid into a gas state, and vice versa? What is the heat required to go from a gas to a liquid? And that's heat of condensation. And we'll see that these are equal to each other, and these two would be equal to each other, but opposite sign. Now let's look at the heating curve for water. We have the temperature on the left-hand side, and we have the heat supplied. So the heat supplied will increase as we go to the right, and the temperature increases as we go up. See that we increase the temperature, and at the melting point, this is important, it's muy importante. Notice as we keep applying heat, heat is always being applied, but the temperature at this point, at 0 degrees, temperature stays the same, but there's still heat being applied. That is where the heat of fusion is. The heat now goes not into raising the temperature, but goes into melting the solid into a liquid. Once all that is water is liquid, heat is now used to raise the temperature until we get to the boiling point, 100 degrees. And now, even though we're increasing the heat, we still increase the heat. The temperature remains the exact same. All that heat is going into vaporizing, changing now liquid into vapor. Once all that liquid is vapor, then the temperature begins to rise some more. Molar heat of fusion, delta H fuse, or fuzz, is the heat absorbed when 1 mole of solid substance melts to a liquid at a constant temperature. So that temperature remains constant, but the heat is going to melt the 1 mole from a solid into a liquid. That is the heat of fusion. Here are some heats of fusion. We can see these are standards, so we can always use these for any sort of problem we're in. We notice here is also heat of vaporization. So the heat required for 1 mole to go into 1 mole of a liquid to go into a vapor. Now the molar heat of solidification is the opposite, but same value. That is the heat lost when 1 mole of a liquid solidifies at a constant temperature. So notice it's the exact same value, but opposite sign. So the heat that it takes to go into melting a mole is exactly the same as it will take that is removed to make that mole a solid. Now the amount of heat absorbed by a melting solid is exactly the same as the amount of heat released by a solidifying liquid, as we just mentioned. So equal but opposite sign. We're going to use this formula for all these problems in this section. The heat equals mass times delta H of whatever, if this constant is in calories per grams or joules per grams. So this would be mass. And so that means the heat released is the mass times delta H whatever. So when I mean whatever, that could be heat of fusion, heat of condensation, heat of vaporization, heat of solidification. Mostly though, however, we're going to be using this. Now it looks exactly the same, but we're going to be using moles. Sometimes you'll see this equation, sometimes, but most of the time we're going to be using delta H, the heat release, is the moles times this delta H constant. So this is the one we're really going to be using. So delta H, whatever, is in kilojoules per mole. That's a constant we can get from a table, or we might have to figure it out. So delta H whatever is delta H fusion, delta H solidification, delta H vapor, or delta H condensation. So we looked at two of those before. We go back to this. All right, so if we look at this, here's the heat of fusion and heat of vaporization. Now the heat of fusion is the same as the heat of solidification, but opposite signs. The heat of vaporization is the same as the heat of condensation, but opposite sign. So these are the only ones we need. We don't have to look up heat of vaporization, or we don't have to look up heat of condensation, because we can just take the heat of vaporization and we can get the value, but just take opposite sign. We don't need to look up the heat of solidification, because we can just look up heat of fusion and just take the opposite sign. These are going to be the same but equal side. These are going to be same. And then we'll talk about heat of solution. So again, heat of whatever we'll put in there. So meaning delta H will equal the moles times delta H fusion, or mole times delta H solidification, or mole delta H vaporization, or mole delta H condensation. All depends on what we are using. So we can solve really for any of these three. We'll be given two of them, and we'll solve for the third. Let's try an example here. How many kilojoules of heat are required to freeze a 20-gram popsicle? It's a nice size popsicle. We're going to assume the popsicle has the same molar mass and heat of fusion as water. These monkeys are enjoying a nice tasty orange popsicle. Let's go back to that equation. Well, we have delta H equals mole times delta H of fusion. Let's look at what the delta H of fusion is for water. We see that the delta H of fusion of water is 6.01 kilojoules per mole. So we'll just put that in our equation. 6.01 kilojoules per mole. So we have that. Now we just have to find mole. So we're assuming that 20.0 grams of that popsicle is water. So what is a mole of water? So we want mole of water. What is a mole of water? In grams, 18 grams of water. And we multiply that across, and we get 1.1 mole of H2O. Now let's just stick it in this formula here, 1.11. And now we will get delta H. And we get delta H equals 6.67 kilojoules. So it takes 6.67 kilojoules to freeze a 20.0 gram popsicle. So that's how much heat is needed. But is that the correct answer? No, no, no. It's not the correct answer, because we don't add heat when we're freezing something. We're taking heat away. So it's actually the heat of fusion. It's really the heat of solidification. And that's the opposite sign. So this was a negative. Okay, so we have to be aware of what if we're solidifying or we're fusing something. And it's the same value but opposite sign. So really what we did, we took that much heat away. So we have negative 6.67 kilojoules. That's how much heat was removed from that popsicle in order for it to freeze, or how much heat was removed from that liquid in order for it to freeze into a delicious, tasty popsicle. Try another problem. How many grams of ice at 0 degrees could be melted by burning a peanut which contains about 25 kilojoules? Let's go to our formula. Delta H equals mole times delta H. In this case, we are melting a solid piece of ice, so that is indeed heat of fusion. Whereas in the last example, we had heat of solidification, but we just needed to change the sign. So we know delta H fusion of water is 6.01 kilojoules per mole. Now what was given to us, delta H, 25 kilojoules. So this was given to us, and the delta H fusion is given to us. we want to know moles, because from moles we can get grams. So let's figure that out. Let's solve for moles. So that's delta H divided by delta H of fusion equals the mole. And then from the mole we'll get grams. So we have 25 kilojoules divided by 6.01 kilojoule per mole, which equals 4.2 moles. But we want grams, so 4.2 mole of water, 1 mole of water per 18 grams of water equals 76 grams of ice. So when we melted 76 grams of ice, it took 25 kilojoules. Let's look at the molar heat of vaporization. Now this is exactly, well, it's very similar to the molar heat of fusion. It's just the amount of heat necessary to vaporize 1 mole of liquid. There's nothing really more magical or different, except now we're going from liquid to vapor. And again, here's the heat of vaporization. And it's the exact opposite. Heat of vaporization is the exact opposite of the heat of condensation we show here. The amount of heat released when a mole of vapor condenses at the normal boiling point. Equal but opposite sign. So the quantity of heat absorbed by a vaporizing liquid is exactly the same as the quantity of heat released when the vapor condenses.